Welcome to Physics 2 Summarized. In this episode, we're tackling the first unit of physics, fluid statics. Note that I expect you to already know Physics 1 at this point. First things first, what is a fluid? A fluid is basically a liquid or a gas, but if you want to get specific, it is a substance that lacks a shape and is easily subject to pressure. Density, or the relative apportionment of mass per space, is, as you'd expect, equivalent to mass divided by volume, and in this class is primarily measured in kilograms per meters cubed or kilograms per liter. Sometimes it's useful to know the specific gravity of a fluid, or its relative density. This is the density of the fluid divided by the density of water at 4 degrees Celsius and 1 atm of pressure. Why 4 degrees Celsius? It's because that's the lowest the density of water can be given standard air pressure. If you've taken chemistry, you know that the hydrogen bonding between water molecules in their crystal lattice structure causes ice to be less dense than water, even though the general trend for matter is to get more dense as temperature decreases. The density of water under these conditions is 1,000 kilograms per meters cubed, which is a value you basically are going to have to use in every problem for water, especially if the density is not specified. Why do dense things sink? The answer has to do with pressure, or the amount of force applied over an area. This is measured in Pascals, which is newtons per meter squared. Consider holding a thumbtack between your index finger and thumb. Even if you push with equal force, the finger touching the pointy end hurts more than the other because there's less area contact and therefore less pressure. That's a quick way you can remember the relationship between force, area, and pressure. When a fluid is at rest, or hydrostatic equilibrium, the force applied by the fluid upon the submerged object is equal on all sides of the object, and this force is always perpendicular to the contact area. Consider a flat square submerged in water. Let's derive the pressure created by water. We know that pressure is force over area. The force acting on the cube is the weight of the water above it, which is equal to the mass of the water times the gravitational constant. I mentioned earlier that mass over volume is density, and we can use that equation to get the mass of the water is equal to the density of the water times the volume. Since the volume is equal to the height times area, we can cancel out area from the top and the bottom and get that the pressure of an object in hydrostatic equilibrium is equal to the density of the water times the gravitational constant times the fluid depth. This is called gauge pressure. Air also weighs upon an object, so adding the pressure due to air, or P0, which is about 1 times 10 to the 5th pascals, you get absolute pressure. Pascal's principle states that an external force applied to a fluid is transmitted undiminished across its entire body. Basically, what this means is that if the air pushes on the surface of a body of water, the effect is felt all the way down to the bottom. What this leads to is Pascal's paradox, or that static fluids will always have a uniform fluid level, regardless of the shape of the container they're in. We can see this by imagining the opposite. Imagine a lopsided water level. The water at point A is under much more pressure than at point B, and as a result is pushed to B's location. This will keep happening until A and B are at the same pressure or equal water levels. Imagine a milk can. If you drink all the way down to the part where the handle is, you'll notice that the milk in the handle is at the same level as the milk in the can, as a result of Pascal's principle. The important thing to get from this is that fluids will always try to flow from high to low pressure due to this principle. Let's go over some common problems for this topic. Hydraulics. 2 pistons, one large and one small, are connected by a U-shaped pipe filled with an incompressible fluid. On the large piston rests a car that weighs 1,500 kilograms. The diameter of the large piston is 0.3 meters, and that of the small is 0.1 meters. What is the minimum force required to be exerted on the small piston to displace the car? How far is the car lifted if piston A is pushed 5 centimeters? Pause the video and give yourself a few seconds to solve this problem. What this problem entails is basically figuring out how much force we need to apply to overcome the weight of the car. Through Pascal's principle, we know that the pressure exerted on A is the same as the one felt by B. Plugging in the areas, FA over 0.05 squared pi equals FB over 0.15 squared pi. Since the area goes up by 9 times, a shortcut to see this is that 0.05 times 3 equals 0.15, and since they're both squared, 3 squared is 9, FA must be 9 times less than FB, so that proportions are maintained. FB equals mass of the car times gravity, which equals around 14,700 newtons, so dividing this by 9 we get about 1633 newtons. For the second part, we will have to use work. Since the fluid is incompressible, the work exerted on A is the work felt on B. Fa times the displacement of A equals F of B times the displacement of B. Solving this, we get that 0.011 meters were displaced on B. This is mathematically equivalent to taking the volume of A pushed down and adding it to B. U-shaped tube. A U-shaped tube is filled with water and then oil is poured on one side of the tube. Find the density of the oil if the amount poured in it has a height of 3 centimeters and the water on the other side of the tube rises to a height 2 centimeters lower than the oil on the other side. Since the fluid is static, the pressure must be uniform at any given height level. If we choose the point where the oil ends and the water begins and label it A, and on the opposite side of the tube at the same level create a point B, we know that these 2 points have the same pressure. Pressure equals rho GH, and since the G cancels out, we get that the density of water times the height of water on one side equals the density of oil times the height of oil on the other. Solving this, we get a density of 333.33 kilograms per meters cubed. An FRQ experiment requiring you to find air pressure. Design an experiment with the procedure to find air pressure, assuming you have materials common to the everyday classroom lab. One method would be to make your own barometer. Fill up a tub with water, fill up a test tube with water, and thumb over the top. As quickly as possible, flip over the tube into the tub and release your thumb as soon as you come into contact with the water. The lopsided water level you've created will adjust according to air pressure. If you did this right, there's a vacuum at the top of the test tube. The pressure created by the water head in the tube must be equal to the air pressure by Pascal's principle, which you can find using ρgh, manometer. Find the pressure of the gas in the manometer tank depicted if the mercury on the right is raised 18 centimeters. The density of mercury is 13,600 kilograms per meters cubed. This problem is only slightly different from the U-shaped tube problem. The gas is pushing with all its pressure on the mercury on the left, so picking a point 1 there will help us find the pressure. Picking a point 2 on the same level, we get that P1 equals P2, which equals the density of the mercury times gravity times height. Solving this, we get a gauge pressure of 23,990.4 pascals. Buoyancy. The past description of fluids as static is incredibly inaccurate for most real-world fluid interactions. The reality is that unless a block is the same density as the fluid, it will either float partially, completely, or sink completely. The force that determines this is the buoyant force. This force is basically caused by the water that formerly occupied the space that the object holds. So if you imagine a cube in water, the water molecules that formerly occupied the location where the cube sits are now displaced, and due to Pascal's principle, they will want to resolve their pressure differential. This means that they will now push up on the block, creating a buoyant force. The buoyant force equals the weight of the displaced fluid, which equals the mass of the displaced fluid times gravity. Since it's hard to measure the mass of a fluid like that, we can further change that and say that the buoyant force equals the density of the fluid times the volume of the displaced fluid times gravity using the density equations. Let's practice this concept. Problem 1. Determine an expression for the tension of the string holding this block. Since the block is obviously at rest, there is no acceleration and therefore there is no net force. Using a free body diagram, we can see that the weight of the block plus the tension force equals the buoyant force. We can substitute these values and rearrange them to ultimately get that the tension equals the volume of the block times gravity times the difference in the density of the fluid and the object. Problem 2. Due to the buoyant force, an object weighed underwater will apparently weigh less than its true weight. Derive an expression for the density of the fluid given the information in the diagram and that the block is suspended by a spring scale. Again, we can just use Newton's second law and substitute and rearrange. These problems are more algebra practice than they are physics. Ultimately, you should get that the density of an object is equal to the mass of the object times the density of the fluid times gravity divided by the mass of the object times gravity minus the spring force. Problem 3. And the final thing I want to show you is a partially floating cube. See this cube? It is partially floating. This means that the buoyant force equals the weight of the block. Using Newton's second again, we can ultimately get a ratio. The volume of the displaced fluid divided by the volume of the object equals the density of the displaced object divided by the density of the displaced fluid, which in water is the specific gravity I mentioned earlier. You will see a lot of questions involving floating geometry, so make sure you practice that. And that's a wrap for hydrostatics. If you found this helpful, please drop a like and comment any questions you may have, and I'll be sure to answer them. Thanks for watching.